Hello everyone, this is Ashish Jhalani and welcome to Infinity Learn by Sri Chaitanya. Now in this particular session, I would be talking about one of the important concept of application of derivative that would be really handy while solving the problems inside the examination. As I said, it is one of the important topic or the concept that will be important not even for boards or school exam but for any competition exam, whether you talk about IIT JEE or KVPY or any other exam. So without wasting any time, let us further get into it. So before we start this particular session, I have a request to make, right? Now, we need to like and subscribe the channel. Why do we have to like and subscribe? Subscribe so that you get all the updates from us regarding any other forthcoming lectures or workshops, and like for us so that we'll be motivated to make such more interesting videos and workshops for each one of you. So before we continue, let us first talk about the lecture plan. What I am going to take in this particular lecture, in this particular workshop. So as I mentioned, the topic of today's workshop is maxima and minima. So I would be starting with the definition and the understanding of the maxima and minima to the core of the concept. Not just the superficial knowledge, we will try to understand the concept more conceptually, the analytical approach. Then we will talk about the different tests that we can use to find out the maxima or the minima. Definition of global maxima and global minima will be in the list, and at the end I will also talk about the application of these concepts into some geometry problem. All of these understanding we will be doing with some hand-picked problems that I have taken for each one of you. So without wasting our time, let us continue with this particular session. So first of all, over here we are talking about local maxima. Now as the word says local maxima, local means a local, right? It's like neighborhood. For example, in our real lives, we also talk about that he is a local boy or a local hero. Let's say if I talk about a local hero, then he is a hero in the vicinity of his house or the city, right? So a local hero, when we normally use this word, it is meant that a person who is hero among the vicinity. Similarly, a local maxima of a function will be that value which is maximum, which is at a higher level, which is the greatest value in the vicinity. So what do I mean by vicinity for a function? For example, let's say I am talking about a point A. So vicinity of A would be A plus h and A minus h, where h is tending to 0. Similarly, h and tending to 0, we have talked about these concepts when we were doing the workshop on monotonicity. If you haven't watched it, you can watch it on our YouTube channel. It's available right there. So right now, the vicinity of a point x is equal to A is A plus h and A minus h. So if a function is having a maximum value in the vicinity of A, then I would say that there is a local maxima at point A. Let us understand this graphically. So over here, let's say I draw a graph. So let us pick purple color. So let's say I have this graph and I am talking about this particular point. This particular point is x is equal to A. Now if you observe at this x is equal to A, I have some value over here. Let's say this point would be A comma fa. If the function is y is equal to fx, then I can say this point, let me call this point as A. So point A, the coordinates would be given by A comma fa. Now if you observe in the neighborhood of A means the vicinity, right? A plus h and A minus h, where h tends to 0. So in the vicinity of A, there is a point over here and point over here. So this point is basically your x is equal to A plus h, and this point behind the A, that is x is equal to A minus h. Now if you observe, the value of function at x is equal to A is larger than the value of the function at x is equal to A minus h, that is the left hand side neighborhood. Over here at x is equal to A minus h, the value is over here, which is slightly less than fa. And if I look at the value at x is equal to A plus h, now observe carefully, at x is equal to A plus h, my value is over here. So the value is slightly smaller than fa. So can I say that x is equal to a is that particular point where the function is having a larger value as compared to their vicinity? Or in other words, I am having a local maxima at x is equal to a. So in short, whenever we have to find the local maxima, the conceptual definition says that it should be the larger value in the vicinity of that particular point. Now over here I have drawn a continuous function. What will happen if I don't have a continuous function? Let us see in the graph 2. Let's say draw a graph. This is a point. Let's say this is how this graph is. So this is a discontinuous function, right? So I can say at point A the function is discontinuous, right? And it will be a non-removable or a removable discontinuity. Observe it carefully. The left hand limit and the right hand limit both are defined, but the value of the function is something else. So this is isolated point removable discontinuity. Anyways, so over here if I talk about at point A, now look at the value of function at x is equal to a. The value of function would be over here. This is the value of the function. Whereas if I check in the neighborhood of a, whether you take a plus h, you will be over here, and if you take a minus h, you will be over here. So I can say the value of the function at x is equal to a is higher than the value of the function at x is equal to a plus h or a minus h. Hence, I can say this is a case of local maxima. So I think now each one of us knows what is the conceptual definition of a local maxima. It is only in the neighborhood. Apart from those 2 points, whatever the function is in the entire domain, I don't have to care about it. For a local maxima, local minima, we just have to take care of the value of the function at that particular point and its neighborhood. Let us talk about local minima. So local minima, now it is the opposite of local maxima. Local maxima, the value was higher or greater or maxima among the vicinity. So whenever I talk about local minima, then I am talking about the value of the function is smallest in the neighborhood of that particular point. So if let's say there is a point x is equal to a and there is a local minima at x is equal to a, so we can say that the value of the function at x is equal to a will be less than f of a minus h and will also be smaller than f of a plus h. So if I draw a graph for that particular continuous function, so let's say we draw a continuous function, right? It's a U-shaped graph, or you can also call it a parabolic graph. We have also talked about parabolas and quadratic equation graphs in algebra. So this particular point, let's say call this particular point as a. Now if you observe, the value of the function at a is something this, right? Let's say call this as fa. Now if I take a point ahead of a, there is a plus h. Now see, the value of function will increase slightly. And if I move on to a minus h, now a minus h, if you observe, the value of the function is slightly larger than fa. So I can say the value of the function fa is smaller than f of a plus h, and this is also smaller than a minus h. So in short, I can say that fa is smaller in the vicinity. So fa is the local minima. Once again, when you talk about local minima, you have to just concentrate on that particular point and its vicinity. We don't have to worry about the entire domain when we talk about local maxima and local minima. So if the function is discontinuous, let us have a graph over here for a discontinuous function. Let's say one hypothetical function I have drawn over here. Now if you observe at point A, let's say this is point A. Now the value of function at A is defined by that particular dot. So the value of function would be this. This is your fa. Now a plus h means x is slightly larger than a. So slightly larger than a, my value will reach over here. So this is f of a plus h, right? And if I move behind a, there is slightly smaller than a. So I am at a minus h, and for a minus h, this is my value. Now, if you observe in this particular graph, the fa minus h and f of a plus h, the smallest is fa. Hence, we can say we have a local minima at x is equal to a for this particular function. So, in gist of it, local maxima is a point where you have a maximum value in the vicinity, and local minima is a point where you have a value which is minimum among the vicinity. Let us move ahead and try some examples to understand this concept, how to apply this in the problem solving. So, stay with me and we will solve some problems. So, question number 1. Now, question number 1 says there is a function fx which is defined as modulus of x when mod x goes from 0 to 3. With the equality sign at 3 and 0, it is larger than 0. And at x is equal to 0, I have defined this function as 2. So, it is a piecewise function where the definition is from 0 to 3 and x is equal to 0. I have to check the behavior of this function at x is equal to 0. Over here in this particular example, by behavior I mean whether you have a local maxima or local minima. One question that arises in my mind, is it necessary that at every point there will be a local maxima, local minima? No, right? You are absolutely correct. At every point there is not necessary that we should always have a local maxima and local minima. We can have increasing points, decreasing point, or just a constant function. So, let us explore this particular example. So, now first of all, I know there is a modulus sign over here. I should get rid of it because unless and until I have a domain defined for x, I will not be able to proceed with the solution. So, now mod x 0 to 3, now we have studied that if mod x is less than equal to a, then x belongs to minus a to a. So, now I can rewrite this function fx as, so mod x goes from 0 to 3. So, x will range from minus 3 with a close bracket to 3 except 0 because 0 is not included. If you see, there is no equality sign at 0. So, when x belongs to minus 3 to 3 except 0, my function would be mod x, and for x is equal to 0, the value is 2. Now, I can further simplify this and I can say mod x will be equal to x whenever x is positive. So, when will your x be positive? If you observe the range, it is minus 3 to 3. So, I can say when x belongs to 0 to 3 close bracket, this is x, mod x will be minus x when x is negative. So, from minus 3 close bracket to 0 open bracket, and this is 2 when x is equal to 0. Now, see, now I have a simpler version of the function fx. Let us sketch this particular graph to understand whether we have a local maxima or local minima over here. So, I draw the coordinate axis, this is x and this is y. So, my domain is only from minus 3 to 3. So, let me plot minus 3 over here, 0 is over here and 3 over here. So, for 0 to 3 your graph is x. X means y is equal to x, which is a line passing through the origin at an inclination of 45 degrees. But at 0 I have an open bracket. So, I have an open circle and this would be like this. For x belongs to minus 3 to 0, I have a line which is y is equal to minus x. So, line dividing the second quadrant in two parts. So, this would be a mirror image. And at x is equal to 0, the function is at 2. Right? Now, I have to check the behavior at x is equal to 0. Now, observe the value of the function at 0 is at 2. So, the function is giving us a value that is equal to 2. Let me find the value of 0 plus h and 0 minus h. Now, 0 plus h is slightly more than 0. So, my x is slightly more than 0, then I am over here on this line. So, the value would be tending to 0, and 0 minus h, the value is again tending to 0. Now, if you observe at f is equal to 0, I am getting a larger value as compared to f of 0 plus h and 0 minus h. Hence, I can say at x is equal to 0, you have a local maxima. Right, everybody? Let us move on to the next example. Now, the next example says, I have to find the value of b. So, it is an interesting problem. Over here, we have to find the value of b where It is given that you have a local minima at x is equal to 1. Such type of problem you will also find in JEE Advanced or JEE Mains PYQs. Many of the times problems are being asked on the same concept. So I have to find a value of an unknown and I know there is a local minima at x is equal to 1. If there is a local minima at 1, then in the neighborhood of the 1, f of 1 would be the smallest value, right? That is what we mean by local minima. Now over here, let us read the function. Fx is given as minus x cube plus something for 0 to 1, and for 1 to 3 I have 2x minus 3. So over here I can easily draw this 2x minus 3. It's a linear equation, so it has to be a line. So I will draw the curve and I will use the basic definition for local minima and local maxima. So from 1 to 3 I have to draw a line. So at x is equal to 1, if I put x is equal to 1, this value becomes minus 1. So I know at 1 my line would be at minus 1. So let's say this point is 1 comma minus 1. The slope of the line is 2. That means a positive slope. So this would be somewhere over here. So the line will go like this. And at 3, this would be 6 minus 3. So this will be 3 comma 3. Both endpoints are included. So this is the graph for 2x minus 3. Now I have to draw the graph of fx. Now I have a b over here. Now it is being said that at 1 I should have a minima. Now observe your graph. At x is equal to 1, you are having a value minus 1. And if I take x larger than 1, then on the line I have a value which is larger than minus 1. Hence it increases. So I just have to worry about the value of f of 1 minus h. Right? Because if f of 1 minus h is larger than f1, then I can say there is a local minima at x is equal to 1 because the other part has already been taken care of. So all I need to make sure is that f of 1 minus h should be larger than f1. If this happens, then there is a local minima at x is equal to 1. Right guys? So f of 1 minus h. Now 1 minus h means smaller than 1. So I will use this particular function. So what is the value of f of 1 minus h where h tends to 0? So I will put minus, instead of x I am writing 1 minus h plus twice of b minus 1. This is larger than f1. I know the exact value of f1. f1 is minus 1. So this is larger than minus 1. Now if h is tending to 0, this will tends to 1. 1 whole cube will be 1. I have a minus sign. So I can write this as, this is minus 1 plus twice b minus 1 is larger than minus 1. Right? Now it's just a matter of solving this inequation to find out the answer. Let us quickly find it out. So minus 1 will get out. I am left with 2 into b minus 1 is larger than 0. 2 will get cancelled out. I am left with b minus 1 is larger than 0. I'll take 1 on the right hand side. So I have b larger than 1. So now I have the range of values of b, that if b is larger than 1, then this function will have a local minima at x is equal to 1. Either you can write the answer in this form, or you can also write b is larger than 1, so 1 to infinity. Either of the way you can write your answer. Let us move ahead with the session now. So now we have talked about local maxima and local minima, right? And not every time it would be possible for us to draw the graph, right? Because for every function we cannot draw the graph inside the examination. So it has a limitation. So we should have different tests to check whether there is a local maxima or local minima at that particular point. Now the first test that I am talking about right now is the first derivative test. Now if I am talking about the derivative, that means the function needs to be continuous and differentiable. If the function is not continuous and differentiable, then I will not be able to use it because it includes derivatives. So whenever you find a function which is discontinuous or non-derivable, my advice and suggestion to you that use the graph, because for a non-differentiable function, graph is the best approach and the right weapon that you can have with you. So right now over here, first derivative test. So we know it is only possible for continuous and differentiable functions. Now what is first derivative test? Let's say I talk about local minima or local maxima. So let's say I draw a graph, a continuous graph, and I have a local maxima over here. This point is point A. Now see, at this point A, I have a local maxima. Let us try to understand the derivative. You remember the workshop of monotonicity, right? We talked about the slope of the tangent. Slope of the tangent is positive or negative or 0 depending upon the sign of dy by dx, because dy by dx represent the slope of the tangent. So if I observe over here at the point A, when you have a local maxima, if I draw the tangent would be like this, right? A horizontal line, and a horizontal line, the slope will be 0. So I can say dy by dx would be 0 at x is equal to a. Now let us talk about a point slightly higher than a. If I take a plus h, so the tangent would be over here, would be like this. Now if you observe, the tangent or the line is making an obtuse angle with the x-axis. Obtuse angle means slope will be given by tan theta. If theta is obtuse, tan theta is negative. So slope is negative, and slope is nothing but dy by dx. You guys are with me, right? So dy by dx would be negative over here. Now if I talk about at a point which is behind a, that is a minus h, then slope of the tangent would be like this. The tangent will look like this. Now the slope of the tangent will be given by the inclination, and the inclination is an acute angle over here. So acute angle means tan theta is positive. So tan theta is positive means dy by dx is positive. Now if you observe, right, I have figured out an important test for a local maxima. If there is a local maxima at x is equal to a, then your dy by dx will move from negative, sorry, it was positive, then it becomes 0, then it becomes negative. So whenever you have a local maxima, the sign of dy by dx will go from positive to 0 and 0 to negative. So let me write it over here. So dy by dx sign, if there is a local maxima, it would be positive, then it becomes 0, then it becomes negative. If dy by dx changes sign from positive to negative, we can always say there is a local maxima over here. Let us see what will happen if we take a local minima. So I draw a graph with a local minima. So this point is local minima at point A, right? Because at A we can see, or it is pretty obvious that at A we have a local minima because it is the smallest value. Now at this point, once again I have a horizontal tangent. So dy by dx would be nothing but 0, right, at point A. Now if I take a plus h, the slope of the tangent would be like this. The slope of the tangent would be what? Acute angle. Acute angle means dy by dx would be positive. So I know over here dy by dx is positive. And if I look at a point that is behind a, which is a minus h, so this tangent would be like this, right? So now you can observe the slope of the tangent will be given by an obtuse angle, so dy by dx would be negative. So I can write dy by dx is negative. Now if you observe, when there is a local minima at that particular point x is equal to a, the dy by dx is changing its sign from negative to 0 and to positive. So if there is a local minima, what do we have to remember? Dy by dx will change its sign from negative to 0 and to positive. So whenever there is a continuous function, all we need to figure out is what is the change in the sign of dy by dx. If dy by dx is changing from positive to 0 to negative, then we call it a local maxima. And if the dy by dx is changing from negative to 0 to positive, we will call it a point of local minima. So this is what is called as first derivative test and its origin, how it is being originated. Let us apply this in some of the examples. Now the first question, I have been given a function which is x square into x minus 3 whole square, and the question is being asked that you have to comment or find out the points of local maxima or local minima. Now over here I will use the first derivative test. Now if you observe, plotting a graph for this function will not be that easy, right? It will be time consuming. Obviously we all can draw the graph of this function, but it's time consuming, and in a competition exam time is more important, right? So over here I will use the first derivative test to save time. So now we will find the derivative of this function, which is given as x square into x minus 3 whole square. So how do we differentiate this? It's a product of two functions, so I will be using the product rule. So differentiating the first function, keeping the second function as it is, plus keeping the first function and differentiating the second function. Now from this, I can take 2x into x minus 3 common. So we'll be left with x minus 3 from the first bracket, and from the second bracket we'll have x. Let me simplify this further. So we'll have 2x into x minus 3 into 2x minus 3. This is my f dash x. Now I would be using a concept called as wavy curve method, right? Now in wavy curve method, we plot the critical points or the roots on the number line, and we plot the signs alternatively. So I hope each one of you know the wavy curve method. If you have a problem with wavy curve method, there are videos on our channel. That's why I have asked you subscribe and explore the channel. You will find multiple videos over here, there to help you understand the different concepts. So over here I will plot the roots. So I have three roots, right? One for this 0, for this 3, for this 3 by 2. So 3 would be over here, 3 by 2 would be over here, and 0 would be over here, right? Plot the numbers carefully. So this is positive. After every root I have to change the sign, right? Now those people once again are having a problem with wavy curve, right? Either subscribe to our channel or watch more videos on our website. So minus plus minus plus. Now these are the signs for f dash x, that is nothing but dy by dx. Now we have studied, right, in the previous slide, then whenever there is a local maxima, the dy by dx would be this, and when you have a local minima, this is how your dy by dx sign would be. Now observe at x is equal to 0. My dy by dx was negative, it becomes 0 and it becomes positive then. So dy by dx is changing sign from negative to positive. Now if you see from negative to positive, I have a local minima. So I can say at x is equal to 0, I have a local minima. Now at 3 by 2 dy by dx is going from positive to 0 to negative. Right? We always move from left to right. Don't move from right to left. Move left to right. Positive, 0, negative. So I have a local maxima over here. And at 3, minus 0, positive. So my dy by dx is going from negative to positive. So I can say there is a local minima. So this is how we can use the first derivative test to find out the points of local minima and local maxima. So let us try another problem. So now over here I have a different function for you guys. Fx is equal to x by 2 plus 2 by x. And the question says find out the local maxima and the minimum value for this particular function. Remember one thing, we are only finding out the local maxima and local minima. This is not the greatest value or the smallest value of the function. That we'll do in the later part of this particular workshop. Right now we are concentrating more on local maxima and local minima. So now once again I will differentiate this function, right, because differentiating would be easy as compared to drawing the graph. So if I differentiate, f dash x would be what? X by 2, the derivative would be 1 by 2. And for 2 by x, the derivative would be minus 2 by x square, right? The derivative of 1 by x is nothing but minus 1 by x square. So now we have to simplify this. So it becomes 2x square. It becomes x square minus 4. So we'll factorize the numerator. This is a square minus b square, right guys? So I can say x minus 2 into x plus 2 upon 2x square. Now once again I will use the wavy curve method to find out the sign of f dash x. What are the roots? 2, minus 2, and for x square it is 0. But there are two roots, right? So there will be two zeros. Logically, but on the graph I'll plot that 1, 0. So I have a positive sign. When I cross this, I have a negative sign. So when I am crossing 0, I have two roots at 0. So my sign will not flip, and over here it flips again. Once again, if you are having problem with the wavy curve method, do study about inequalities. There you will find wavy curve method. So now these are the signs. Now we have to find the local maxima and local minima. For your help, I will once again plot the curves. For local maxima, this is 0, this is negative, this is positive, this is 0, this is negative, this is positive. Now see, at -2, I am moving from positive to negative. From positive to negative, I know this is a local maxima. So for this function at x is equal to -2, if somebody asks you, you will say there is a local maxima at -2. At 0, it is -2 minus. -2 minus is neither of these two cases. So at x is equal to 0, your answer would be it is neither minima nor maxima. As we discussed before, right, at every point there is not a necessary condition that we should always have a local minima or local maxima. At 0, we have neither of them. At 2, I am moving from minus to positive. So minus to positive is for local minima. So at 2, we have a local minima. So at 2, we have a local minima. At -2, we have a local maxima. And at 0, we have a neither maxima nor minima. Now, are you guys with me? I'll tell you an interesting aspect or an interesting fact over here. See, at point 2, you have a local minima. Let us find the value of the function. So f2 is how much? I'll put x is equal to 2 over here. So I'll get 2 by 2 plus 2 by 2. So I'm getting 2. Right? So local minimum value is 2. Let us find out the local maxima. What is the local maxima? Local maxima is occurring at x is equal to -2. Let's put x is equal to -2 over here. So -2 upon 2 plus 2 upon -2. Isn't it? It's interesting. At a local maxima, I am getting a value which is negative, and at a local minima, I am getting a value which is equal to 2, which is positive. So always remember, right, this proves that local minima and local maxima are only in the neighborhood. That is not on the entire domain. I hope you guys are with me and you guys are enjoying and learning this particular session. Let us move ahead. So test 1 we have talked about. Now what is test 2? Test 2 is kind of a conclusion from the test 1 only. Remember the test 1. I'll draw the test 1 graphs over here. So test 1, when we talked about local maxima, you remember we talked about dy by dx, and we said dy by dx is equal to 0 over here, positive over here and negative over here. This is dy by dx. Right? And for local minima, let me draw a graph for you for your understanding. So over here dy by dx was 0, over here it was positive, and over here it was negative. So these are the signs for dy by dx, right? And we have checked dy by dx in the first derivative test to find out whether it's a local minima or local maxima. But over here I am saying that second derivative test is nothing but a conclusion of first derivative test. Let me make you understand. Now in the workshop of monotonicity, we talked about increasing and decreasing function. And in increasing and decreasing function, I have told you that whenever there is a function which is increasing in nature, the dy by dx will always be larger than 0. And whenever there is a function which is decreasing in nature, dy by dx would be less than 0. So in short, if a function is increasing, I can say dy by dx is positive, and decreasing dy by dx is negative. Let us observe over here. Now, think dy by dx to be a function. So dy by dx is some function, right? Now this function, as I move on x, this function is moving from positive to 0 and 0 to negative. So the value of dy by dx is going from positive to 0 and negative. So we can call this function as decreasing function, because from positive I am moving to negative. So if this function is decreasing, so using the concept of increasing and decreasing, I can say the derivative of this function will always be negative because it's a decreasing function. So the derivative of dy by dx would be what? d2y by dx square, and d2y by dx square would be negative, and this becomes my second derivative test. So instead of finding out dy by dx plotting on the wavy curve, I can also find it out the double derivative of this function. If the double derivative at that particular point is negative, I can say at that particular point I am having a local maxima. So if you have to find a local maxima, differentiate the function and get the critical points. At those points, try to find out the d2y by dx square. If it is positive, right? Sorry, if it is negative, then I can say it is a maxima. And if it is positive, then over here. So over here, if you see, dy by dx is changing its sign from minus to positive. So the value is negative, it becomes 0, it becomes positive. Hence, it is called as an increasing function. And whenever we have an increasing function, the derivative of that function needs to be positive. So over here, I can say the derivative of the function was dy by dx. Remember, dy by dx is showing a increasing nature. So the double derivative would be positive. So whenever you have double derivative positive and dy by dx 0, we can call it a local minima. And when double derivative is negative and dy by dx is 0 at that particular point, we call it a local maxima. So for local minima and local maxima, we can also calculate the double derivatives of the function to figure out. Now, a question comes to my mind, is it necessary that we always get double derivative as positive or negative? Sometimes it might be possible that I am getting double derivative also 0. Then what to do in such cases? We will be stuck. In such cases, we will generalize this second derivative test and we call it a nth derivative test. Now, nth derivative test is simple, right? Do not go by the definition, understand the logic, what logic follows over here. So, nth derivative test says if dy by dx is 0 and d2y by dx square is also 0, let's say d3y by dx cube is also 0. So what will you do? So the nth derivative test says if you are finding the derivative 0 and after a certain point, after a certain derivatives, let's say you figured out fna, right? So fna over here is nothing but nth derivative of the function, right? So there is a function, you differentiated it, at point A it is 0. Then you double differentiated it to find out the d2y by dx square, it is again 0. And you are differentiating it every point, you are getting it 0. And when you have done the nth derivative, so if n is even, right? If nth derivative, if n is even, so if it is positive, I call it a local minima. If it is negative, I call it a local maxima. So when n is even. Now, to remember this, let us go back to the second derivative test. The second derivative test says double derivative. Double derivative means even, right? This is even. So when it's even, the signs will give me whether it's a local minima or local maxima. That's why I said we are generalizing this. Generalizing this for n. If n is even, you have a local minima and a local maxima depending upon the sign of dy by dx. Secondly, if n is even, sorry, there is a mistake over here. So we all are human, right? That proves. So if n is odd, neither maxima nor minima will occur. So even after differentiating and you are getting a value over here for n is equal to odd, we can say it is neither minima nor maxima. Let us understand this with an example, right? Because with example we would be able to understand this concept beautifully. So now I have a question over here. So let us first do a question on the nth derivative test. Right? Don't worry, we'll move on to that particular example as well. First of all, I am here to help you understand the nth derivative test. Now, nth derivative test, I have a function, right, fx. So first of all, I will differentiate this. So if I differentiate this, x raised to power 5, the derivative would be 5 into x raised to power 4 minus 20x cube plus 15x square. This is the derivative of this function. Let us simplify this. I can take 5x square common. So now I am left with x square minus 4x plus 3. I can factorize this 5x square into x minus 1 into x minus 3. This is how we can factorize f dash x. right? Now, Shivam Sikawar, हेलो बेटा, तुम लोगों के लिए यहाँ पे मैं हूँ, यहाँ पे सिखाने के लिए, राइट? आई एम देयर फॉर ईच वन ऑफ यू. सो लेट अस कम बैक टू दिस पर्टिकुलर सॉल्यूशन, राइट? सो मेरे पास f dash x कितना है? 5x square into x minus 1 into x minus 3. So 5 dash x is this. So if I make it equal to 0, from here I will get the values of x is equal to 0, 1 and 3. So these are the 3 points or 3 values of x where dy by dx is equal to 0. Now I have to find out the second derivative test to check at which of these points I have a local maxima or local minima. So let me differentiate it again. So f dash x. So f dash x would be what? I have to differentiate f dash x. Where is f dash x? This is f dash x, right? So I will differentiate this, or we can differentiate this function, right? This is also f dash x, or we can differentiate this function as well. All of them are f dash x. If I differentiate this, try to understand. Over here I have to use a product rule, right? There are 3 parts. Over here I also have to do a product rule, 2 parts. Over here it's a polynomial, derivative would be easy. So we need to be smart inside the examination hall as well, right? So I'll take f dash x in this format and I will differentiate this. So f double dash x would be what? 20x cube minus 60x square plus 30x. So now you can take 10x common. You are left with how much? 2x square minus 6x plus 3. So now we have to check the sign of f double dash x. Now at x is equal to 0, check f double dash 0. It is 0. It is neither positive nor negative. So I cannot comment on f x is equal to 0 whether you have a local maxima or local minima. So I will not be able to comment. What is f double dash 1? Now if I put 1 over here, this is positive. This is 2 minus 6 plus 3. So this is negative. Negative into positive is negative. So now I can say at 1 I have a local maxima, right? Because we have a double derivative as negative. Now double derivative of 3. Now if I put x is equal to 3, this is positive. 3 square, 9 2s are 18. 18 plus 18 becomes 0 plus 3. So once again I will have a positive sign. This is positive, product will always be positive. So f double dash 3 is positive. So it would be local minima. So with the help of second derivative test, I could figure out there is a local minima at x is equal to 3, local maxima at x is equal to 1, but at x is equal to 0, f double dash 0 is 0. Now we'll use the nth derivative test. If your double derivative is 0, you differentiate the function again, the function which is f double dash x. So now I will find f triple dash of x. So once again I will use this function, this polynomial for the differentiation, not the product one. They are same, right? So we can use either of them. So f triple dash x would be how much? 60x square minus 120x plus 30, right? Now if I put 0 over here, f triple dash 0, now I am having a value 30 that is positive, but the derivative is odd, and it is defined that if n is odd, then it is neither maxima nor minima. N needs to be even, then only we can say whether we have a local maxima or local minima. So now I can say at x is equal to 0, I have neither maxima nor minima. Now let's say in some possible case where f triple dash x comes 0 and the fourth derivative at x is equal to 0 comes down as positive or negative, in that particular case we can obviously say whether we have a local maxima or local minima. So now I hope you have got the understanding of nth derivative test. So let us move back to that particular example that we have left, fx is equal to sin 2x minus x. Now over here I will use the derivative test. So first of all I will differentiate this function. So what is f dash x? The derivative of sine 2x. Sine of 2x, I have to use a chain rule. Sine of 2x would be cos of 2x into 2 minus 1. Now this f dash x needs to be 0, right, for the local maxima or local minima. So from here I can say cos of 2x is equal to 1 by 2, right. Now x belongs to where? 0 to pi, right. So x was 0 to pi. Now if I multiply it by 2, then 2x is from 0 to 2 pi. So cos of 2x, so this angle will go from 0 to 2 pi. So cos of 2x is equal to half. So I need to write down all those values where cos will be half. So cos is positive in the first and the fourth quadrant. So I know the 2x will be from the first and the fourth quadrant. In the first quadrant, 2x will be given by cos is half. At what angle? It is 60 degrees. 60 is pi by 3. And in the fourth quadrant, it is at 2 pi minus pi by 3. So if I simplify x from here, I'll get x is equal to pi by 6. I have divided by 2. And over here, x will be equal to pi minus pi by 6. Pi minus pi by 6 would be 5 pi by 6. Right guys, so now I have two different values of x, one is pi by 6 and one is 5 pi by 6. Both of these x lies between 0 to pi, but we have to check the local maxima or the local minima. Now over here we'll use the second derivative test and I will differentiate the f dash x. So if you differentiate this, we will get f double dash x. Now what is f double dash x? Would be derivative of this function. Now derivative of cos x is minus sin x. So I can say derivative would be 2 cos of something is minus sine of something into derivative of 2x is 2 minus 1 is 0. So I can write f double dash x would be nothing but minus 4 sine 2x. This is your f double dash x. Now I need to check the values at pi by 6 and 5 pi by 6 to judge whether I have a local maxima or local minima. So f double dash of pi by 6 would be how much? Minus 4 sine 2 pi by 6 would be pi by 3. Now sine pi by 3 would be an acute angle, first quadrant, value would be positive and there is a minus sign. So I have a negative value. So if double derivative is negative, I know there is a local maxima. So I can write over here, I have a local maxima at x is equal to pi by 6, right? Now at x is equal to 5 pi by 6, I will find the value of f double dash, f pi by 6, this will be equal to minus 4 sine 5 pi by 6 into 2, that becomes 5 pi by 3. Now 5 pi by 3 would be 300 degrees, which lies in the fourth quadrant. So sine would be negative. So if this value is negative multiplied with a negative sign, so finally I will have a positive value. So double derivative at x is equal to 5 pi by 6 is positive. Hence we can say there is a local minima at x is equal to 5 pi by 6. So I think now you are pretty much comfortable with the nth derivative test, first derivative test, second derivative test and their meaning and their approach. Let us move ahead. We've already solved this. So now we're done with the local maxima and local minima. So now we're talking about the global maxima and global minima. Now what is global? Right, global means the across the globe. So I am talking about the complete set or the complete domain if I talk about in terms of function. So what do I mean by global maxima? Global maxima means that particular value of x for which I have the maximum value in the entire domain of that particular function and not just in the vicinity. In the vicinity, I have a local maxima, local minima. When I talk about the entire domain, we talk about the global maxima or global minima. In many of the problems in physics and chemistry, you might have heard greatest value, least value. Greatest value is basically your global maxima and least value is your global minima. So global maxima and global minima, if I draw a graph, try to understand the global maxima and global minima. That is plot a graph so this point is A, B, C, D, E, right? So I have drawn a rough sketch for you guys. Now if you observe over here, there are certain values. Now if I talk about at point C, observe at point C. At point C you can see a local minima, right? Because the value of function is lowest in the vicinity. So this is local minima. So this is local minima. At point D, there is local maxima, right? Now if you observe at point E, I again have a local minima. Right? So from this particular graph, I can say that local maxima and local minima, it is not necessary that we should have only one local maxima or one local minima. You can have multiple local maximas and multiple local minimas. It is possible, right? There can be a possibility where you don't have a local minima, local maxima. So local maxima, local minima can be any number of points. It can be 0, it can be 1, it can be more than 1, right? Local. But when we talk about global, right, the global maxima is the one which is the one, right, which is the ultimate, greatest value, and the least value or the global minima is that smallest value which is smallest in the entire domain. So smallest in the entire domain cannot be 2, cannot be 3. The maximum in the entire domain cannot be 2, cannot be 3, it has to be 1, right? So global maxima and global minima will not be more than 1. Now if you observe this particular graph, the greatest value that this function will have is occurring at point A. This is your global maxima. Right? At A. Whereas at A, I don't have a local maxima or local minima because there is no neighborhood. Now, if you talk about the global minima, where do we see the smallest value? Smallest value is over here. So this is global minima, right? So I have both the possibilities in this particular graph. A global can occur at your local minima as well, or global maxima can occur at global maxima, local maxima, right? Your global maxima is over here where there is no local maxima. So global can occur at any point whether there is local maxima or not, right? तो अगर मैं इस ग्राफ को सिंपल वर्ड्स में समझाऊं तो लोकल मैक्सिमा लोकल मिनिमा कितने भी पॉइंट्स पर हो सकते हैं, राइट? एक पॉइंट पर, 2 पॉइंट पर, ऐसा भी हो सकता है आपका लोकल मैक्सिमा ना हो या लोकल मिनिमा ना हो, right? Global maxima, global minima can occur at any number of points. They can either occur at your local maxima, local minima, or they can occur at some other points as well. Now, one important aspect that we should remember about global maxima and global minima is that the global maxima and minima will occur at a definite x and they should give a definite value of y. Now, over here the emphasis on the word definite. Global maxima or minima should occur at definite x and a definite y. Now, what do I mean by definite? Let us understand this with the graph. So, I have already drawn a graph for you, and in this graph I have to comment on the global maxima and the global minima. Now, if you observe in the entire domain, this graph is defined from -1 to 3, and if I look this graph from -1 to 3, I can see that the minimum value that I will get is at x is equal to 3, which is 0. So, I can say, okay, so this is nothing but global minima. So, global minima is occurring at x is equal to 3 and the value of the global minima is 0. Now, let us find out the global maxima. Global maxima means maximum value. So, where do I see maximum value in this entire domain? So, this is increasing, 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 it increases over here, then it decreases. So, I have a maximum value over here. So, my maximum value is occurring at 2, No, it is not occurring at 2 because at x is equal to 2, you have this value. The maximum value is occurring at 2 minus h. Now, is 2 minus h is a definite value? No, right? Because h tends to 0. 2 minus h, for example, let's say if I ask you what is 2 minus h, you will say 1.99. But then I will say no, it can be 1.9999. Then again I will say 1.99999 and so on. So you cannot catch 2 minus h, hence it is not definite, right? Similarly, the value of y, let's say if this point is 3, for example, right? The function will not achieve or will not attain the value of 3. It will be slightly less than 3. It will be slightly below 3, it is 3 minus h. So the value of y is also not definite over here. Let's say if x is definite, for example, the y is not definite because I cannot say I have attained 3. I am below 3. And how much below I cannot define because it is tending to 0. Hence, over here in this particular graph, I can say that global minima do occur at x is equal to 3, but global maxima will not occur. So there is no global maxima for this function. Right? So there can be a possibilities where your function will not have a global maxima or global minima only on one constraint where the function will either x is not definite or the y is not definite. Right? So always remember this catch, because in the examination hall when you are solving problems, the examiner will try to trap you in such kind of traps, in such kinds of conceptual knowledge. So if you understand global maxima and global minima that it should occur at a definite x and a definite y, you will always get your answer correct and you will always get +4 or +3, whatever marks are being allotted. Right? So now one interesting example that I have picked for you over here, because this involves local maxima, global maxima, but there is another aspect behind taking this particular equation, because such kinds of equation you will find everywhere in functions or in calculus part. So we should be able to comprehend this equation. So in this particular example, I would be doing the complete postmortem for this particular function so that whatever comes in your way, you guys will be able to answer it. So stay with me and let us explore this. So my function is fx is equal to twice of modulus of x minus 1 plus 3 times modulus of x minus 3. Now we all know the function modulus x. Modulus x means I will always have a positive output. So when x is larger than 0, mod x is x, and when x is negative, mod x is minus x. So can I say the function modulus x will change its nature whenever x becomes equal to 0, or in other words, the function inside the modulus becomes 0. So over here I can say the nature of this x minus 1 modulus, it will be changed when x minus 1 becomes 0, which means at x is equal to 1. So at x is equal to 1, this modulus of x minus 1 will change its nature. Right guys? Similarly, modulus of x minus 3 will change its nature at 3. So now I have two important points for this particular function where the modulus of x is changing its sign. One is 1, one is 3, and my function involves both of them. So how do I proceed? I draw a number line, right? Because we know it conventionally, right, that for any function to solve, I need to always remove the modulus sign. If modulus signs are removed, now it becomes a cakewalk for us. So I will also try to remove the modulus sign, and stay with me and let us learn how to remove it. So x minus 1, my first critical point is 1 and the other critical point is 3. So x minus 1, I am writing about modulus of x minus 1. So modulus of x minus 1 will change its nature at 1. So before 1, modulus of x minus 1 will be opened as minus x minus 1, and after 1 it would always be x minus 1, because if x is larger than 1, no matter what x you put, this will always be positive. So I can write after x larger than 1, it will always be x minus 1. Now same is the story for mod of x minus 3. Mod of x minus 3 would be negative when you have a x less than 3. So over here, let me write mod of x minus 3. This is 3 minus x this is 3 minus x, and once I cross 3, it becomes x minus 3. Right? So I have represented mod in all these three areas, right? No worries. Let me remove it. Right? So first case is this, when x is less than 1. So when is x is less than 1, I am writing the function now. Function would be twice of this plus thrice of this. So twice of mod of x minus 1. Instead of this, I can write 1 minus x plus 3 times 3 minus x. Right? So this is for x less than 1. For x lying between 1 and 3. So between 1 and 3, this can be written as x minus 1 and this can be written as 3 minus x. So my function would be twice of x minus 1 plus 3 times 3 minus x. Now when x is larger than 3, these are the values for mod. So let us replace them, twice of x minus 1 plus 3 times of x minus 3. Now if you see, I have the function fx over here without the modulus sign. Now we'll just simplify this. So let us quickly simplify this. This becomes how much? 2 plus 9, that is 11, minus 2x minus 3x is minus 5x. This is for x less than equal to 1. Now this is 2x minus 3x. So that will be equal to minus x. 9 minus 2, that is 7. This is for 1, 2, 3. And for x larger than 3, let us simplify this, 2x plus 3x, that is 5x, minus 2 minus 9 minus 11. So now this is your fx. Let us draw the graph of this fx. What are the points? 1 and 3. Right? So now for x less than equal to 1, the function will be given by 11 minus 5x. So at x is equal to 1, the value would be 11 minus 5, which is 6. So at 1, I know my graph would be over here. Right? This point is 1, 6. Now 11 minus 5x, if you observe, it's a linear equation with a negative slope. So it will be a line with a negative slope for x less than 1. So like this. And ending at 1, 6. So between 1 and 3, I have 7 minus x. So if I put 1, 7 minus 1 would be 6. So this line also starts from 6 with a negative slope, but with a less negative. And at x is equal to 3, this reaches 7 minus 3, 4. So now the slope will decrease a bit. Right? This is how the line would be. Now at x is equal to 3, this is 15 minus 11, once again 4. So it starts from the same point with a positive slope. So this is 3, 4, and it starts with the. So this is how the graph of fx will look like. Now try to understand, if I have the graph, I can do everything with this particular function. If somebody asks me the area, I can find out the area, of differentiability, continuity, anything you ask, right? I have everything ready if the graph is being shown. Now I have to sketch the graph that is being done. I have to comment on the local and the global maxima and the minima point. Now you observe, this is local minima. So local minima at x is equal to 3 and the minimum value is 4. Now the local minima is also your global minima. Right? Because at this point I am also having a global minima. Do I see a global maxima? No, because global maxima will go towards infinity and infinity is not a definite value. So no global maxima. Right guys? So I don't have a global maxima over here. Local maxima, I don't see a local maxima as well. So there is no local max. So in this particular graph, I have no global max, no local max, but I have a local minima and global minima which is occurring at the same point x is equal to 3 and the minimum value would be 4. देखो आया पूरा का पूरा क्वेश्चन सबको समझ में? So let us move ahead. Now, one interesting question to ask right over here. Read it carefully and answer me correctly. Is it necessary to have a global maxima at a point where local maxima exist? Right? No, because global maxima can occur at a point where there is no local maxima. Remember the graph that we have done? At the end point we have a global maxima, but local maxima was not there. So the answer is false. It is not necessary. Second, is it necessary to have local maxima always larger than the local minima? So the question says, क्या फंक्शन में हमेशा ऐसा होगा कि लोकल मैक्सिमा हमेशा लोकल मिनिमा से बड़ा है? बिकॉज वहाँ मैक्सिमा दिख रहा है, वहाँ मिनिमा दिख रहा है. नहीं होगा, राइट? बिकॉज वी हैव ऑल्सो डिस्कस this in the example. Remember 2 by x plus x by 2, local maxima was smaller than local minima. या फिर मैं इसका एक रियल लाइफ एग्जाम्पल देके सोचूं, मान लो एक बैच है, there is a batch A and there is a topper in that particular batch. So the topper of that batch is basically your local maxima. There is another group, another class, another batch, and there is a local minima, right, in that particular batch. Can I say that local minima is smaller than that local maxima? No, right? ऐसा भी हो सकता है, this local minima, this group is a group of top and brilliant student. This is the second set of students. So the local maxima of this particular group would be smaller than the local minima. So local maxima and local minima, there is no relation between them. Anyone can be larger than anyone. So if somebody says local maxima is always greater than the local minima, the answer would be no, it's not true. So now we have come to the part where I am taking some examples on the geometry, that how to use maxima and minima concept when geometry comes into picture. So over here I have picked an example which says a sheet of area 40 meters square is used to make an open tank with a square base. Find the dimension of the base such that the volume of this tank is maximum. Right? Easy peasy question. So we don't have to worry about this. So let us have a square base or a tank over here. So the tank has a square base. So let's say this is your base and I call this as x. So this will also be x. And let's say this height is y. It's an open tank, so there is no surface on the top of it, right? So the total area is 40 meters square. So let us find out the area. One, I have a base. The area of the base would be how much? It's a square. So area of the base would be x square plus the area of this surface. This is x and this is y. So area of this rectangle would be x into y, and we'll have 4 such surfaces, right? The 4 walls. So I have total area of 4xy. This should be equal to the total area of the sheet that I have used. So this becomes my first equation, x square plus 4xy is equal to 40. Now what do we have to find? We have to find the volume and we need to make it maximum. So if volume needs to be maximum, we have to differentiate the volume. So I need to find out the volume in terms of some variable. So what is the volume? Volume of this tank would be area of the base into height. What is the area of the base? X square. What is height? Y. So now I have to differentiate a volume to find out its maximum value, but I have 2 variables x and y. I need to remove one of them, because for differentiation I need only one variable. How to remove? I have an expression over here. So from here I can see calculating y is easy as compared to calculating x. So I am finding out y. Y would be 40 minus x square upon 4x. And this y I will replace over here. So volume becomes x square into what is y? 40 minus x square upon 4x. So 1x will get cancelled out, and if I multiply, I have 1 by 4 over here, x will be multiplied, so 40x minus x cube. So now you see I have a volume in terms of x only. I have to find out the maximum value. So let us quickly differentiate this with respect to x. So 1 by 4 is 1 by 4. I have a 40 minus 3x square. So dy by dx needs to be 0. So I'll get x is equal to plus minus under root 40 by 3. So now I am getting two different values. Now x cannot be negative, right, because it is a side of this particular tank. So how can x be negative? So I can say from here that x needs to be root of 40 by 3. Now I have to check whether I have a maximum or a minimum value at this particular x. So now I have to differentiate dy by dx. I am using the second derivative test to find out the answer over here. So what is d2v by dx square? So let us differentiate this. So I have a 1 by 4, derivative of 40 is 0, minus 3x square, the derivative would be minus 6x. Now if x is positive, the bracket becomes negative. So negative value into 1 by 4, this is negative. So double derivative is negative, so I know it is a local maxima. Right? So at x is equal to root 40 by 3, I will have a maximum value. I need to find out the dimension of the base. So x is root 40 by 3 and this is your answer. And let's say if in the question they ask about the y or the maximum value of the volume, y, you can calculate y from this expression, put x is equal to root 40 by 3, and if it asks the volume, then you can find out the volume from this particular expression and you can put x is equal to root 40 by 3. In this particular example, the question says dimension of the base only. Right guys, so we are clear till this particular point and we are moving ahead towards the end of this wonderful session. Towards the end, not the end, we have one more problem for you. Now in this problem it says there is a right circular cylinder is inscribed in a given cone. Find the dimension of the cylinder such that its volume is maximum. So I have to maximize this volume, right? Volume for the cylinder which is inscribed inside a right circular cone. So first of all, let us have a cone. So let's say this is a cone and let me draw the periphery, right? So this is a cone. Now I have to inscribe. Inscribe means a cylinder has to be inside the cone. So a cylinder needs to be inside the cone. So let's say right, this is how the cylinder would be, right? Now if I draw the height, now this height of the cone, let's say this is h, the radius of the cone, it is r. Everything about the cone is being given, right? Because it says in a given cone. So I know the h, I know the r. So h and r are the known over here. Now let's say cylinder, the height of the cylinder we call it as y and this we call it as x. The radius of the cylinder, right? It is only this part is x. So now I have to maximize the volume of the cylinder. So let us first write the volume of the cylinder. Volume of the cylinder would be pi x square into y, right? Area of the base into height. Area of the base is a circular base. So pi x square into y. Now if I have to differentiate this, there are two variables. Same story, I need to find a relation between x and y. Now how to find a relation between x and y over here? Now over here we will be using a very interesting concept that we have studied in class 9th or 8th, right? Called as similar triangles. Now how to use similar triangles over here? See, now this is a triangle, right? Let's say I call this as A, this point is B and this point is C and this point is D, so D, E. Now see, ABC and DEC both are similar triangles. So if two triangles are similar, I can always say the ratio of their corresponding sides are equal. So what can I say over here? H upon R, side of the triangle upon side of the triangle, the big triangle I am talking about. Now this should be equal to smaller triangle DEC. This height is y upon this length is how much? The complete length is r, this is x. So this would be r minus x. So now I have a relation between h, r, y and x. From here we can calculate the value of y. So the value of y would be h by r into r minus x. Remember, h and r both are constants, so I don't have to worry about them. Now y is given as in terms of x. So over here, so let us put the values. Y is equal to pi x square. What is y? Y is h by r into r minus x. So let me simplify this for you. Pi h by r, all these are constants, right? So this is x square into r minus x. Now if I multiply this, pi h by r into r x square minus x cube. Now this is the volume for the cylinder. So if I have to maximize this, we all know what to do. We have to differentiate this with respect to x. So pi h by r, this becomes 2rx minus 3x square. Now if I term this as 0, from here I'll get x is equal to 0 or 2r by 3. Now x can never be equal to 0, right? Because if x is 0, the cylinder, the base will be 0, right? So obviously x is 0 is not allowed. So I am having only one value of x. So first I have to check whether the volume is maximum or not, right? So d2y by dx square. So I will differentiate this particular expression. It becomes pi h by r is nothing but the constant 2r minus 6x. Now if I put 2r by 3, now at x is equal to 2r by 3 d2v by dx square. I am sure it should come down as negative because I need to find out the maximum value. Otherwise, how will we find the maximum, right? So logically I know it will come down, but still will prove 6 into 2r by 3. So this is how much? Pi h by r, this is 2. So I have minus 2r. So it becomes minus 2 pi h. See, d2y by dx square is negative, and if the double derivative is negative, I know there has to be a maxima. So we'll have a maximum value for x is equal to 2 pi by 3, and we need to find out the dimension of the cylinder. So x is the radius, so the dimension is 2r by 3. I also need to find out the y because it is being asked dimension. Dimension also includes the value of y. Now what is the value of y? We'll get the value of y from here. Put x is equal to 2r by 3. So it will be h by r into r minus 2r by 3. So it becomes r by 3, r will get cancelled out, so we have h by 3. So this is the dimension of that particular cylinder where radius is 2r by 3 and height is h by 3. Now with this we have come to an end of this particular workshop where we talked about maxima, minima, its conceptual definition, understanding, application, different derivative tests and its application on the geometry, right? So I hope you guys have enjoyed. In the next session, I would be taking you to a different world altogether. See, till now in the calculus, we have learnt about limits, continuity, derivability, application of derivative, differentiation. So what is the use of all these concepts, right? Why do we need to study all these particular topics? The application of all these topics together is important to make sure that we are able to sketch the graph. In the next coming session, I will be taking you to the world of sketching. Till then, enjoy your day, stay safe, and don't forget to like and subscribe our channel. Thank you so much, guys.